You're listening to SEEK Bytes, a podcast for software engineers by software engineers. On this episode, we're talking about the art of competitive problem solving and how a sleep-deprived engineer beat AI at its own game. We talk about the competition itself, how we won, how the AI coded, and a whole bunch about AI, which we're going to be talking a lot more about on Season 3 of SEEK Bytes. Welcome back to SEEK Bytes, Season 3, the first episode of Season 3. It's me, Will.
We're back, baby.
Let's go around the table. Who have we got today?
We've got Elliott in the house, loudmouth as usual.
Seamus, here as always.
Arnav.
Arnav's new. Welcome to the podcast.
Thank you.
Today, we are going to be talking about how a human beat an AI in a competitive coding competition. And we're going to talk about briefly competitive programming, just kind of as a whole, what it is, different types. And then we'll go into this competition. But what I really wanted to talk about, and something the other articles that I found didn't go into, is the breakdown that the winner of this competition wrote. He wrote how he went about the problem and how he ended up winning, and also his take on the AI's work as well, which I thought was way more interesting than just kind of talking about the competition generally.
Firstly, what's competitive programming?
Yes. Well, competitive programming is they have a whole bunch of competitions, and at the moment, @Coder is kind of the biggest of those sort of providers.
@Coder.
Yes, yeah. AT. And so there's kind of two types of competitive programming categories. There's like the algorithm-based ones, which is kind of like a whole bunch of elite code problems. You essentially solve it or you don't solve it. And you kind of do multiple, and I guess whoever does the best. The other type is an optimization type of problem, in which case they get given one problem and they just have to optimize it as best they can. And in this competition, that's kind of what they did.
So when we say optimize, my knee-jerk reaction is either speed for execution or like the amount of memory used or a combination of both.
Yeah, I mean, that's what lead code mostly just cares about as well, right? It's just how, like what your time complexity is, what your space complexity, and that's it.
Yeah, so these are called like NP hard problems. That's basically kind of what they're doing. So they're a special class of computational problems that are believed to be impossible to solve perfectly in a reasonable amount of time, even with the most powerful computers. Think of it as the problem grows, the time needed to find the perfect solution explodes significantly. So what might take 1 second for 10 items could take years for 100 items. And so that's kind of the problem they had here. So the competition, it was the World Tour Finals 2025 in heuristics. Yep. It was kind of like the big one. And it was held on the final day after many of these programmers and coders had already been competing for 2 days prior. So keep in mind, a lot of these people may have been sleep deprived, and the winner himself was, as he said, very sleep deprived.
For anyone who's not aware, heuristics you can think of heuristics as being the strategies that AI or even human brains take to simplify problems. So like chess, for example, let's say like breadth first search, depth first search, like these can be forms of heuristics. It's just the strategy that you're using to not have to solve the entire problem and get close enough to an answer.
That's right. So in this case, the problem was you have a 30 by 30 grid, and you can have up from 10 to 100 robots around this grid, depending on the seed and depending on how you want to do it. And basically, each robot had to get from point A to point B. Each robot had a different point A and B, and they all had to get to their destination at the end. And they had to, if they got to the destination and moved away, that didn't count. They had to like stay there. Everything had to be in their final place at the end. And so, of course, you can imagine that as you add more robots, they're around the grid. How do you make an algorithm that can be solved to fit all of them optimally, basically?
And is it not just fit them? Does it also like measure the number of moves taken to get them there as well?
That's exactly it. So it's meant to be the least amount of moves possible to get them to their final destination.
So the assumption is you'll get a random seed, so they'll be randomly around the place. They'll have a random assortment of where they need to get to, and presumably it's predictable to the point of, given this seed, this is the expected minimum number of moves. So they kind of like know what they're trying to calculate to.
I have a little visualization for the people here of essentially what it would look like. It really is just a 30 by 30 grid with a whole bunch of dots around and lines pointing on where those dots are meant to go. Yeah, there's a whole bunch of seeds that change the orientation. And so they would be given some test data that they could use and a whole bunch of things.
I would be terrible at this.
So everything gets given a starting position and a targeted end position, basically. Yeah, okay.
This is AI 101 as well. Like this was one of the first problems that they give you when you're in uni and studying AI.
Interesting. Yeah. Did you study AI much?
Yeah. Yeah, I did a master's in data science. So
amazing. Why am I only hearing about this now? I've known Arnav for like 2 years and like this is the first time this knowledge bomb's dropped.
I start signing my emails with this now so that everyone knows.
Yeah. Perfect host to have. So they had to measure the amount of like moves, and each move was whether you move the entire group as one or you move little sections of group as one, that counts as one move. Essentially one command, up, down, left, right. Those are the moves that they can give them.
Does that, dumb question. Does that mean that if I move one robot, that's a move, or if I move all of them, that's a move, or is it you move all of them with a single command? Like you say up and all of them move up?
Up. If you just say up, whether you move 1 or 100 robots, it's just one move. It's just essentially one command, I guess. Yeah, sure. If you want to.
So what I was wondering is like, can you, like, if you had 100 different commands for the different robots, that's 100 commands?
Yes.
It's not just one execution. It's each different command.
Each different command is one execution. Basically.
I think it's also in like isolation per robot as well. Like it's basically just finding the optimal path for one specific robot at a time. So
how they could also use walls. They could place walls freely between moves and stuff like that. However they wanted, if they could. There was no penalty to placing walls to like stop the robots moving in certain directions. And that was another part of the problem as well. How could you like place walls in a way to get them all to move the way you want, essentially? So the reason why this is hard is with 100 robots, each having different start and ends, the number of possible solutions is astronomical in a 30 by 30 grid. There's also no like known perfect algorithm for something like this. So there was 12 programmers. These were like very, very smart people. And OpenAI was a sponsor of the event. And so they decided to add an AI to one of these. It was the first time ever that they've had an AI compete in one of these events. That was kind of the premise. I don't even know. That would freak me out if like you're going into a coding competition with an AI as, and not just an AI that's been trained specifically on this as well. It was a custom model that they made to be able to solve problems like this.
Yeah, we're not talking about like an LLM here that's like you ask, what's Bezi or Cursor or something, and it's trying to figure out based off of a bunch of documentation what it should say back to you. This is an actual like targeted specific problem solving AI.
Mm-hmm.
Yeah.
Because that's a whole different ballgame. Because if it was just, by the way, Cursor is going to be running in agent mode against you, that's a lot less terrifying than it's like, no, we've custom built one. Like we built the
This is like Stockfish. This is like
equivalent.
Stockfish in chess, right? Like Stockfish is like the big bad AI in chess world. So this would be like that for these coding problems.
I haven't heard of Stockfish. Is that the new champion?
It's the one that all like the chess YouTubers mention all the time. They're like, if they're talking about a new AI, they're like, let's see how it goes against Stockfish.
No.
Yeah, it's one of the stronger like chess AIs.
Yeah.
See, I'm just showing my age here. I just remember Deep Blue, like the supercomputer that was made to. It was like first one that could beat grand champions.
It beat Kasparov or something like that.
Yeah.
Yeah, something like that.
And they were like, we've done it. We've replaced humans at chess.
I mean, that's kind of how this story is a little bit like, isn't it? I mean, man versus AI, except man won. And who knows how long this will be able to keep happening with man be able to win.
Was it just one person? Like, because you said there were 12 human participants,
yes.
Yeah? So it was just one out of the 12 that beat the AI as well?
Yes, only one person. The AI came second in that competition.
So it is scary then. Because
it is.
It's like we were pretty close to losing completely, right? Yeah.
And these are like very, very smart people who are doing these. So the winner, I'm going to butcher his name and I'm very sorry. I wrote it down. Przemysław Debiak is the best I can pronounce it. He's Polish. His online name is Sayo though, so I'm going to keep just calling him that. So basically the competition, was held in Tokyo. It was a 10-hour competition, which really kind of sounds like a work day, but when you're already sleep deprived and not feeling up to it, 10 hours straight coding is a heck of a lot of work. And this was, from what I understand, the first on-site competition from AtCode that they've done. So they're all flown to Japan and they did it on site. And they actually had it was all streamed live, so you can watch the entire 10-hour stream. And they had what was like a confessional booth as well, so they could go in and talk about how they were doing, and they kind of wanted them to do that.
Like on those game show reality shows and stuff where they like Love Island and stuff, where they pull them to the side and they're like, Brad's being really mean. It's just like, that AI is terrifying me right now.
Absolutely, yeah. I don't think there was quite as much drama, but
yeah,
it was cool. I did watch one of them that Sayo did. I'll come to that in a moment. So he actually used to work at OpenAI as well. Like years ago, he worked on OpenAI 5, which I think worked. It was like one of the AIs that beat a bunch of Dota 2 players, I believe.
Oh, right, yep.
So he used to work for OpenAI, and now he's beating them at their own game, which is kind of great. So the rules of the competition as well, I just wanted to kind of go over. They individual contestants, so there was no communication allowed amongst the other contestants. Access to the internet was fine, except for social media. Screen sharing was used to detect collusion. They could all use their own laptops. However, when they write and submit it, everything would be run on one judge's machine. So everything would be run with the same conditions, same machine, time, memory limits, all that stuff. They were given provisional ranks as they went, and they could submit as many times as they wanted, but there was a 5-minute a delay between submissions. Which meant they could kind of see how each of them were going as they went. They could see how the leaderboards were going. There was no time limit on the external compute for local testing, and they were allowed to use generative AI as well themselves, except apparently a large number of them didn't really use them, apart from auto-generated tab completes and stuff like that. Yeah, and there wasn't really much preparation they needed to do either, apart from just some scripts to kind of help load things into the testing environment, really. To me, that feels, I would have read up. I would have, I don't know, done some sort of preparation on some of these things, because these are quite complex problems that we're talking about here.
Was the problem known ahead of time?
Yeah, that's what I was wondering.
I believe so, because on the actual website, it does say what the task is. You know what? I'm not too sure. I don't want to speak confidently on that.
I would imagine it would be more fairer if they didn't know what the problem was before they went in, right? Because otherwise you could just research and be like, what are the best algorithms?
I guess, but then also the AI was trained on something. So the AI then has an advantage because it was trained.
Yeah, or is it trained on understanding time and space complexity? Is it optimized? Is it built to understand algorithmic complexity and how to reduce?
I believe it was trained on similar problems like this.
Yeah, so it might not have ever seen that problem. It's same as the humans, right? They've solved big O notation related NP complete, NP hard problems before. They've worked in this problem space, but they haven't seen this specific problem. That's my assumption, right?
That's actually really interesting. You said they built an agent specifically for this, right?
Yeah.
It would be interesting to know what the training data was. Because if they have access to lead code problems and the solutions and all of the information that's out there, then it's just unfair, right? It already knows the solution. It's just trying to make it work at this point.
That's right, yeah. And also how much budget and stuff they had. Apparently the AI had about a few $1,000s of budget. And there was a separate budget for testing because the all the competitors had to test their code. So they had a separate budget for how much they could do there as well.
That's a really interesting potential limit on the AI there. If you're saying that, it's handicapped, it can only spend $1,000 worth of tokens. I suppose the benefit is that, you couldn't spin up 1 million of them and just be 1 million monkeys riding for 1 million years. Eventually you'll get the perfect
brute force it, just try to get
They're trying to create a constraint similar to the human brain, right? We don't have the ability to just infinitely expand our resources to solve a problem. So don't let it do that too. But then the challenge is how many tokens is the equivalent of the human brain?
That's a big question, hey. But it doesn't even have to be the equivalent of the human brain. I think one thing just reading some of Saya's stuff, is he said, he had a great quote here. AI might not be the smartest right now, but it's definitely the fastest. Sometimes multiplying a single average person many times produces a better result than a single special human being.
Yeah, there was a study recently as well which said that like it was basically just trying to validate whether like agents make junior or graduate devs like write professional code, and the outcome was something along the lines where it said not always. It just said like it's doing well if the person knows what they're trying to achieve and like what the constraints are, what they're trying to actually what the professional code looks like. But then if not, they're just pretty much vibe coding. And
because you can't judge it, right? Like you don't know what good looks like, so you're just like, this looks like code.
Yeah, and so in this problem as well, if there were no constraints and like the question was not actually very descriptive and the agent didn't have a lot to go on, it could have just hallucinated and like written a very terrible job. But then I'm assuming the question in itself also had guidelines around what is the outcome and like what the results are trying to compare, like, oh, we should just get the best time complexity or space complexity and stuff. And that basically just makes it more like aware of what needs to be achieved.
That's the gap right now, right? Like that's the main thing that separates us from the AI coding tools, is that we're able to work with things we've never seen before and make inferences from totally disparate, unrelated data, where AI are like, if they haven't seen it before, then like what are they dealing with? Like they have to, I'm not aware of AI being able to like make inferences from something they've never seen before based off of like other stuff. I think it's all just like everything they've seen, they can compress together and then figure it, like normalize or average out the right answer. Like it looks at 100,000 reports, averages out, which of them are saying the same things. And then based on like if 80% of them are saying the same thing, it's figuring out that answer right there.
Yeah, it's just probability. It's like, it doesn't even care about the cohesive answer that it's giving you. It just cares about the next word that needs to tell you.
And that's what like AGI is, right? Like once we have an AI where they can do that, they can solve problems they've never seen or never been trained on and have no like base of information to build on. That's like the singularity event. Yeah.
I can't wait because I'm really looking forward to AI making breakfast for me and not burning my house down.
Yeah, breakfast you've never even seen before.
I can't wait.
But then next time you're in Kmart, you look at a sandwich maker, which is like $20 and you get it. You don't want the AI version of it.
Yeah.
I just had a thought. Did WALL-E come out before TikTok and before like short form videos?
Long before.
So WALL-E kind of predicted the brain rot. All those people in the floating chairs staring at their phones like, ooh, just giggling at like dumb videos. WALL-E like predicted the future of humanity.
Yeah. And they all become incredibly fat because all they do is float around and eat and watch videos.
Yeah.
So back to this problem. So Saya, he's done a lot of these competitions before. He's won a lot of them before as well. But he says he really did not get enough sleep. And he says one of the things he recommends going into one of these competitions is being well rested. So unfortunately, he didn't quite get that. He said over like the last 3 days, he got maybe 5 hours of sleep.
Wow.
Ooh, brutal.
Right, that's rough.
Yeah, I mean, the competition didn't need any sleep. So
yeah, well, that's exactly right. AI doesn't need any sleep. But the other 12 competitors did. So, maybe who knows how sleep deprived they were. Because he was feeling tired, he basically said, I'm not going to do anything too complicated because one, he just doesn't think he could have been able to at the time. So instead, while most of the competitors went about trying to create separate groups of the robots to navigate them, he thought the most optimal way of doing things was just making all the robots move at once, giving one command and having all of them move that one direction. And that, I think, was kind of what set him apart, is that seemed to be the optimal solution at the time.
Move everyone up. Now everyone right. Now everyone left, and hope that you eventually hit the sequence which gets them all into the ideal spot.
Because you could set walls as well.
So you can move more with less commands and then add constraints to stop how far they go.
Yeah.
So it'd be a planning problem then, right? To try and figure out the right series of walls so that you could move everything uniformly and have the right ones not move and then move. This is like in
I feel
Zelda
like that's
games.
just layering on top of the original problem.
In like top-down RPG games, this problem exists on a really small scale. It's like they often do it on ice fields, and there's like pillars that you've got to slide in a up, down, left, right direction, and you got to get them onto the right spot. And they'll keep moving, and they'll go past the spot you want them to stop. This sounds like that problem, but like at a much larger scale.
It's just Pokemon game. That's what it is.
Yeah.
It's every Pokemon game up to like Gen 6 had this problem. You'd get to like some floor and then you'd just be sliding around and then you got to drop the boulders down and blah. Yeah.
I know the traveling salesman is another similar one of these problems where the salesman has to get to each house as often as possible.
Has to visit every destination at least once with the most optimal route, right? Yeah.
That's actually one of the solutions for this as well. Like the most brute force ways of doing it would just be like doing a breadth first or a depth first search.
Well, yes, because now that you mention that, I actually want to mention the things he implemented, and you touched on breadth first. So he always used a single group. He used a fixed path for the whole group because it was easier to implement and might be good enough. And the goal is to find placement of the walls, which is a very hard problem, so that when all robots move along the same path, they finish in a position that is somewhat close to their final position. And then as a final step, use a breadth first search for each robot to move them individually to its final destination.
Yeah, right. You put a wall above any robots that have their destination above them. You put one below the ones that have them below, and then when you move up, the ones that actually need to go down don't move, and the ones that need to go up are up. And then when you want to go down, the ones that don't. Yeah, that kind of problem. Okay, interesting.
The thing about the traveling salesman thing is like underneath it, it's sort of using Dijkstra's, however you pronounce it. And one of the concepts of solving this problem is like you already know where you are and where you're going. You basically try to figure out what the shortest path is between both of these. And then your movements sort of just mimic where this line is going. And so like if you hit a wall, say you're trying to like go right, but then you hit a wall, you go downwards if the end goal is a little downwards, and then you still try to find your optimal way around it. And so I guess this is one of the things that you could use in something like this as well, because you have all the different starts and ends.
Yeah, isn't Dijkstra's you check your neighboring node's distance to your destination? So like if you're at a point, you check all the places you can go, and you check which one of those results in you being closer to your final destination, and you take that one, and then you just repeat that over and over and over again.
Yeah. I know A star is meant to be similar to that, but it's
A star
slightly
is
worse.
like, it's basically just going both ways and like trying to
find where they
out.
connect. Yeah.
You basically weigh out all the options and then figure out which the lowest one was.
Well, A star is actually important because when he finished his solution, he said a quicker way to optimize this was when performing a breadth first, do an A star instead to speed it up. And so what's interesting is I haven't quite got to there yet, but at the end, 24 hours later, they put his code into OpenAI, the same model that kind of they used for this, to see what it would do, and it ended up fixing those two of his like main recommendations that he was surprised with. It implemented A star and it implemented something else, which I can go over.
I think I was describing A star a second ago, actually. I think A star is the one where it looks at your neighbors and sees which one's closer and then picks the one that's closest. And then what you're talking about is it's like an enhancement on that where they optimize it by doing it in both directions. So you treat both the destination and the start as being the user, and then you do them simultaneously. And when they meet, you know what your path is because you've used half the path and half the path. I think I was describing A star actually, yeah.
Yeah, I remember doing this at some point, like breadth first, depth first, A star, Dijkstra's when I was doing AI at uni, but we were in the Wampus world, and so you're moving a little link around. And
I did the Wampus world thing as well, yeah.
Yeah, and then it was like you could also get the fairy to send out. So there were two ways. One was you don't know where you're going; it's a blind search, and the other one was you can send the fairy out to try and find your destination first.
Yeah, there's probably a lot of computer science students going, I forgot about the Wampus world. Oh my God.
Yeah, a lot of these terms I actually hadn't heard before, so I'm really glad you guys can explain them a little bit. But another thing he mentioned was being able to just set walls. It simplified the whole complex problem to just placing walls, really. He still had no idea how to do it efficiently, but he decided to do the simplest possible thing. So he decided to perform the hill climbing, and in each step simulate the whole movement and use a sum of the Manhattan distance as an eval function. Now that sentence makes no sense to me.
I think Manhattan distance is two-line direct. Like Euclidean is straight line, right? Euclidean is like pretend there's nothing in between. You go straight to it. What's that distance? I think Manhattan is like
Euclidean. What?
Right, okay, yeah. Euclidean distances, you just take 2 points and you calculate the distance between them like as if there was nothing in between them. I think Manhattan distance is like north, south, east, west. But I could be wrong on Manhattan distance.
It's been 4 years.
It's been a while,
more you know.
yeah. It's been 7 or 8 years. It's taken me back.
I tried to look into it, but it's I think too much to.
It's
go
too
into.
complex.
Yeah.
I miss studying computer science. It was fun doing all this stuff. It took me it wasn't until third year where it like clicked. Oh, this is all theoretical. It's all theoretical. They can't actually exist. It can only exist in your mind. It can't actually practically exist. Like they talk about engines that build engines. And that's the goal. So like you can build an engine that builds agents, for example, but once you can build the engine that builds the engines that build agents, you can solve anything. You can build an agent that can do anything. So like that's the real problem to solve. I love that kind of stuff. So Manhattan distance, did we get?
Yeah,
No,
it is. It is actually what Seamus said. It's like the absolute distance between two things, which is like sort of in a grid-like structure. So
Gotcha. He also mentioned hill climbing, which I didn't really know, but he said hill climbing here just means he was randomly adding and removing walls and keeping the changes that improve the score.
Run it, see which walls helped and which ones didn't, and then swap the ones that didn't and do it again, and swap the ones that didn't and do it again.
Yeah.
Until you're only left with walls that
That
made it faster.
Does anyone want to take a guess how long it took him to get to a working solution?
How many hours real life it took him to get something that actually found that solved the problem?
The first working solution, yeah.
10 hours.
Well, it was a 10-hour competition. So it wasn't 10 hours.
Educated guess.
I don't know. I feel like an hour and a half, maybe. Like maybe he's like, here's a working one really quickly, but it's not efficient.
Yep. Seamus, you gonna...
He went this simple problem, right? So he wrote some code that just moves everything simultaneously. And then he said he randomly placed walls and then figured out where to keep them.
Yeah.
I feel like it was fast. I feel like he got something that worked in
fast.
minutes. And then it was, because I've done this before, like when I studied AI at uni, finding something that works is not the problem. It's optimizing the hell out of it till it's actually usable in a normal amount of time. That's where all the challenge is. So I'm guessing like, I don't know, half an hour.
Not quite. It was basically an hour and a half. It was an hour and 40 minutes. I mean, to me, that's
still impressive.
That's still very impressive.
Yeah,
you hear about a problem and 2 hours later, you've got code that solves that
minutes.
problem. That's crazy, right?
They were able to run the problem for many times as they want, but there was a 2-second time limit. So constantly he kept adding data and testing it. And so he was always like measuring basically the speed and how many samples. So from his very first sample, he had about 40K sims he was able to get in the 2 seconds. And then over the next few hours, he started making some incremental changes, speeding it up to get it from 40 to 120K sims on average, switching hill climbing to simulated annealing, and I don't even know. SA is what the acronym. I can't even say that word.
Simulated annealing.
Annealing. Yeah, okay.
What's annealing? Oh my God.
Yeah, okay. There's going to be a lot of concepts here that we're not going to be able to get into.
I thought annealing was when you, like, I'm thinking of blacksmithing, when you like heat up a metal so it's really hot and then you kind of bang it into shape while it's still warm.
Oh, yeah.
Because there's quenching when you then put it into water, but I thought annealing was the shaping of the thing once it's hot and malleable.
Yeah, so simulated annealing is a probabilistic optimization technique that finds the global optimum of a function by mimicking the physical process of annealing in metallurgy, where a material is heated and then slowly cooled to reduce defects and reach a more stable state. So the idea is that it's constantly being run and then cooled to reach a stable state. Now, what does that actually mean in terms of code? So it works by starting at a high temperature, allowing the algorithm to accept worse solutions to avoid getting stuck in a local minima, and gradually reducing the temperature to decreasing the probability of accepting bad moves until the system settles into a stable. So you make it more accepting of errors until it reaches a stable point, and you just reduce the threshold for error acceptance.
You know, that is really interesting because I've seen that in action with, and this is slightly tangential, when people are trying to write an AI to like beat simulated Pokemon games, and it's like they've dumped the AI in there without having any input whatsoever. So they've never seen the game, they're just seeing pixels for the first time, and then they're like, here are your options to move. And basically they're like, initially they were like, you can do anything. And so it was just like walking around in circles. And then they had to add kind of restrictions about, well, if you see new pixels, then that's warmer. So it makes them more likely to do that. But I also remember they hit some certain point and there was like an animation happening.
Yeah.
And then it got stuck just sitting next to the animation watching it.
I saw that same video. Yeah, I remember, like, because it was trained on new is better. Whenever the animation was treated as like super high value because it was refreshing pixels over and over and over again. And so it like ended up just staying in this town, and just that they described it as like childlike wonder being lost in the mystery of this digital world. It was just wandering around the town like, look at all the pixels. Oh my God, look at the flowers. Because that's right, the flower was animated, right? They moved. And so that town had more value than any other town because everything was animated, which is funny because that's not too different to what a kid would think. Like this town is more exciting to be in because it's moving.
Well, from there, he really just tried to optimize as much as he can. And a big breakthrough he had is when he increased the budget. So they really had a 2-second thing. So locally, he decided to give it 20 seconds and see how it performed. And what he found was it actually increased his score by about 25 to 30% doing that.
So it got better over time. With given a little bit more time, it was able to get more efficient over time.
Exactly. Doing that, gave him a score that was slightly more than he needed to match OpenAI score. So that his main bottleneck he found was the simulation code. Everything else was kind of negligible.
So just to take a step back, the simulation was to determine the actual series of steps. And that's what they were ultimately judged on, is how many steps it took. So it doesn't matter as long as their solution to calculate those steps was under 2 seconds. Because conceptually it sounds like, and I think I am misinterpreting, but it sounds like he removed that time limit so that he could spend more time to simulate to get the best outcome. And then once he found that best outcome, he ran it through whatever the program was, be like, execute this series of steps, which resulted in like the minimum number of steps computed and the maximum.
So you have 2 seconds, see how quickly you can solve as many as you can. So it's obviously
it's not just solving one, they're just going to keep pumping different inputs.
Oh, yeah, it's going to randomize, and you've got to solve as many as you can in that amount of time, which is an indication of how performant it is, right? Because given a 2-second window, the same amount of data, and the randomization is exactly the same. It doesn't matter how it's randomized because you're all dealing with a grid the same size. It doesn't matter if you get a different sequence than me. The point is that you went through 100 variations.
Yes. And so and this reminds me, when they were testing it, they were giving like 100 samples. But for the actual final results, there was like 2,000 tests that they had to do. So I guess it was just how many could you go through and how many moves?
So his must
like
optimize itself. Like it must start with no weightings, and then it runs and it builds up weights, and then those weights get more and more accurate.
Yeah, that's what the global optimum function thing does. And
so he does go a little bit more into like how he optimized it, which if you're interested, it's on his GitHub. Actually, it's on the @Coder GitHub, @Coder, and then under AWTF 2025. Anyway, so he really good article, but he was able to optimize it immensely from 120k sims to about 70k sims just from kind of realizing what he had to do. 700k sims, which was quite a 15% leave over the next human competitor, but was still just behind the AI. But he was kind of in a weird spot at about 7 hours and 20 minutes in. He finally managed to pass OpenAI's score, and that's when he went and did his first recording in the confession room just to say something. And I watched this, and he looked so tired. He was just talking just to kind of get it out. And I remember one thing he said was like, yeah, OpenAI, your bot sucks. Which I thought was hilarious. Just the confidence on how well he was doing. Because he went in he said maybe a 5% chance of winning is what he thought was at. So clearly he thought he was doing very well. And at this point, he felt quite confident that he could make something that would win.
When you think about it, when you zoom out a little bit, it's like 12 people flew to Japan to compete. So this is like people who take this very seriously, and it beat 90% of them, right? It beat 11 out of 12 people.
Mm-hmm.
I don't know. Maybe the bot's not that bad. Maybe it doesn't suck that bad.
I agree.
Following up on the other 11, did they all succeed in providing a solution that met the criteria of the 2-second limit?
Yeah. They all did very well. They all did very, very well.
But they just maybe weren't getting like a million iterations, a million sims or something.
So Cyro's score was 1.8 million, or is that billion? It's a really big number. The OpenAI's was 1.6, and the one below that, the one is 1.4. So, I mean, they were all they were pretty close. It was like a 9% difference between Cyro and OpenAI's score.
Yeah, that's trillions. That's in the trillions.
Oh, trillions. Okay, great. Yeah.
But the bottom one there is only in 430 billion. So
yes, yeah.
But that still was within the limit. So that really tells you about optimization, doesn't it? No matter how much you optimize, you can still optimize further.
The difference between 500 billion and 1 trillion is so massive.
He said he had a lot of ambitious ideas, but due to his tiredness, he decided to skip anything he couldn't implement in less than 5 minutes. I think what really helped him was he just did anything he needed in the easiest format he could, just to make something work and make it optimal. I want to finish off with what happened at the end of the competition. So clearly he won. There was a prize for it as well, a monetary prize. At the end, he kind of wrote some things that he could have done better. One thing he didn't account for was like pre-built walls, which some of the seeds seemed like they had. When performing, like we said earlier, when he was doing the BFS or the breadth first search, do A* instead to speed it up. There were some other improvements instead as well. But afterwards, one of the finalists spent some time to kind of improve his solution and ended up improving it 2 times better.
Ooh.
But the AI also, I want to talk about just the AI a little bit and how it went about, because he also looked at all the solutions the AI submitted, and I thought this was really interesting. The first thing was it introduced changes very widely in terms of quality. Many submissions were near complete rewrites. Even when the changes were reasonable, about 10 to 30%, they usually touched multiple unrelated sections of code. And additionally, there are a few submissions that are equivalent to changing a constant. So the AI submissions, there were 27 submissions. The 23rd and the 27th submission were identical. And some of the submissions, nothing changed. Some of the submissions, very little change. Other submissions, everything changed. It was very wild in terms of how it was submitting.
So it wasn't methodical.
No, it doesn't sound like it.
You would expect, like, I don't know, I think you would naively assume that an AI, it's an AI, it's intelligent, it's a machine, it's robotic, it's methodical.
Mm-hmm.
Why would it not iterate one thing at a time? Because that's what we do as engineers, right? Like we always talk about, like, when you make change, you don't want to just blow the world up and do everything at once, because it's very, very hard to test everything.
Mm-hmm.
So this AI was just saying, no. Like, my job is to go fast, and you go fast by breaking things.
Mm-hmm. Yeah, after a while, there were only 2 main solutions that the agent kind of had, submission 26 and 27. Both of them based on beam search, but they shared no similar code. He said this supports maintaining a wider set of solutions that are developed independently. The code also got, as you can imagine, very progressively more complex and less maintainable. Most of the late improvements are rather small tweaks. The agent nearly plateaued during the second half of the contest. There was only about a 4% improvement during the last 4 hours. The last 2 points he mentioned were that the latest submissions of the AI had very little white space. He thinks that it's just a weird temporary side effect of rewriting the code many times in a row, and then it just eats some of the white space and just continues on. And finally, all the magic numbers in the code were very round. Rather than trying to like tweak it and find the the best fitting constant, the agent had the tendency of adding more complex code rather than tweaking some of these little values. He also said, like, the provisional tests that they had, his code submission at 7 hours in, when he finally like beat it, would have beaten it in the end. It wasn't as back and forth as he thought it was. It's just that small sample size made it seem that way. But once they made it, that they did the full sample, the 2,000 seeds or whatever it was, his would have beaten it right at the 7 hour mark. In conclusion, basically they did give the AI his code later, and it did improve on it, which I think just goes to show that, like, using AI in tandem with an engineer who knows what they're doing can be really good. There's a lot of things it can find as well that it might be able to help improve your code and even just speed you up and stuff like that. One final little pop quiz. Does anyone want to guess how many lines of code this final solution was? He did clean up some of the the junk, but does anyone want to take a guess?
400.
400?
I'm going to guess 1,000.
1,000?
150.
150. 708. But I imagine with some of the extra stuff, it probably would have been closer to 1,000 at first.
Nice. That was a good start to talking about AI. We're going to be talking about AI for most of season 3, right?
It's going to be an exciting season, yeah. And yeah, it is going to be more AI based, but that is kind of the world us engineers are kind of, living through a little bit.
It's moving fast. It's moving very fast.
It really has exploded since episode 2, when we season 1, where we talked about ChatGPT. Like, it has gone so far. Like, I remember saying for then, I was like, I want something that can search my code base. That would be useful, not this like chat window. And it's like, we have that and so much more now.
I think in that episode, we were talking about the Will Smith spaghetti AI image generation thing.
yeah.
That's the one that I find a lot of people benchmark is like the early image generation was like this horrendous Will Smith monster eating pasta, and it's just like got 8 arms, and it's just can't. And then a year later, it's like a perfect representation of Will Smith eating pasta, and I'm like, I think we talked about it in that episode, and the same leap has happened again. We've gone from these rudimentary-ish chatbots to now they can code.
Thank you for watching. We'll see you next time on SEEK Bytes. Listening.
Because what are they watching?
What are they watching? You're watching our voices. Thank you for listening.
What are you watching? I want to know now. Write in. What are you watching?
If they have that like synesthesia ailment or whatever, it's that you see sound.
Yeah.
Like you see color, like your brain interprets sound as color.
Yeah.
Just for those people, thank you for watching.
When you get a concussion, that's one of the things that happens.
Bye-bye.